Jeez. Oh God. Shit. Sorry, camera's on. So, hi, my name's Anthony. You may know me from various places. You may see me at the office or something like that. But it came up that there was an issue around floating point precision, and I thought I'd do a quick video just to explain some of the technical detail behind it. So, yeah, let's get stuck in. So, we're going to be using paper and a whole bunch of ink in order to explain the problem. It's just easier to sort of go through things just while I can sketch things. So the first thing we're going to start is a quick breakdown of what a decimal number looks like. So we've written these down like they've just become habits. So let's pick something. Let's pick 367.291. Now this is going to be a fairly standard number. It's nothing special. I've just picked it up by random. But we're going to just represent it in a slightly different way. And that's going to be 100% equivalent, but we're going to draw it like this. So 367.291 is hundreds, tens, ones, and tenths, hundreds, thousands. So it's like being back in primary school, which is 3 times 100, 6 by 10, 7 by 1. And then at the decimal point, we're going to do 2 lots of tenths, 9 lots of 100ths, and 1 1,000th. Right, so nothing particularly controversial here. It's just breaking this number up into a different representation. Now, I'm just going to quickly change. You'll actually start seeing there's a pattern here. Right, before the point to the left of it, so in this section here are numbers greater than 1. The other direction to the right, numbers less than 1. It's going to rewrite this slightly. So if we rewrite this as this is another equivalent kind of representation. 6 by 10 to the 1, 7 by 10 to the 0, the dots here, 2 by 10 to the negative 1, 9 by 10 to the negative 2, and 1 by 10 to the negative 3. Now, if you hadn't noticed, there is a very clear pattern here, and there's a very clear pattern here. Right. This is just another way to express what we have as a decimal number. Now, this also equally applies to binary. We're going to do the same thing. I've chosen another binary number, which is 101.011. I'm going to write it exactly the same way. So before the dot, we are looking at 1 by, in this case, should be 4, 0 by 2, 1 by 1. The dot comes into play again, and then after the dot it's 0 lots of halves, 1 quarter, and 1/8. So if I replicate this pattern here, it looks like this. 1 times 2 to the 2, 0 times 2 to the 1, 1 times 2 to the 0, decimal point, 0 times 2 to the negative 1, 1 times 2 to the negative 2, 1 times 2 to the negative 3. Now, if this representation doesn't make sense to you, that's fine. It's not particularly critical. What I'm just doing here is demonstrating that there is actually a pattern. It's very easy to see here because it's 10, 100, and 1, and then tenths, hundreds, thousands. It's less obvious to see here if you're not familiar with binary numbers, but if you are familiar, you'll notice these are all powers of 2, which is exactly what we're showing here. And also just some quick terminology, we're referring to these as decimal numbers. Just going to grab another color just for fun. So this is a decimal representation of this number. So this is decimal. And this here we're calling binary because it is. We're not making this up. All right. So in decimal, we're saying also, we're calling it base 10 and binary base 2. Now in base 10, we have 10 separate symbols, which happen to be 0, 1, 2, up to 9. Binary for base 2, we have 2 symbols and 2 symbols only, which happen to be 0 and 1. The base here is this number here. You can see all of them here. So in a base 10 system, we use tens here. All right. So again, that's a pretty basic refresher on how to represent numbers. Now, hopefully you will notice the patterns that are occurring here. because now we're going to talk about accuracy, which is probably why you're here. Click on the page. So accuracy. Let's not worry about binary for a second. Let's look at decimals. Now, numbers can be represented in a number of ways. So simple ones we've looked at previously are fractions. So let's take some couple nice clean fractions. A quarter is easily 0.25. A half, make that actually legit, 0.5. And let's do an eighth. Right, these are all chosen because I can do the math in my head. 0.125. These are all perfect, clear representations. Now, a quarter is always going to be precise. A quarter of a donut is a quarter of a donut. Half a donut's half a donut. An eighth of a donut is pretty miserly and you should probably buy a couple more. But there are other things that we can do that are impossible to perfectly represent in this fashion. So let's say there's 3 of us. I have an extra subscriber and there are 1 donut. So we're going to do thirds. Right, so what is a third? It's not 0, it's 0.3. It's kinda there. If we say 3/10, we still have 1/10 left over. So let's divide the 1/10 by 3 again, which means we have 3. And we will have, this repeating kind of number. At some point, you run out of paper, you run out of ink, or more accurately, you run out of patience. So this number here is always going to be an approximation of this precise concept. We have other things like this. So for example, 1/6. 1/6 has the same problem. 1/6 is roughly 0.1666666. I'm getting bored. 7. You can see that it should be 6 forever, but because we're rounding it up, 7. So this and this representation are not identical. This here is always going to be an approximation, right? And this kind of is one of the basic problems. There are things that we can describe perfectly in one system that we cannot describe perfectly in another system. And if we go into binary, binary is another system. So let's look at some fairly let's look at a classic straightforward example. So in decimal, we're going to do this, 0.1. That is our number here. What does that equal? It's 1/10. That is also precise. There is no quibbling about this value here. They're going to be the same forever, right? In binary though, what is this? So, all right, let's look at the binary representation. Now, remember we're talking about quarters, halves here. So I've basically prepared this little cheat sheet, which we're going to run off. All right, so let's put this off to one side. Let's move the cheese out of the way. So we know that 1/10, so let's take this number here, or 0.1 equals what in binary? Well, obviously it's 0 because there's 0 here. 0 point something. Is it a half? No. All right, so can't be that. Is it a quarter? No. 0.25 is still too big. Is it an eighth? No. 0.125 is still too big. Is it a 16th? Well, it's definitely more than a 16th. So, all right, let's mark that here. Okay, we still have a leftover, so it's about 0.0375 we're missing. 1 on 32? Huh, okay, we can add that as well. So now we're much closer, but we still have a leftover remainder. And obviously that remainder is going to be much bigger than this, which is bigger than this. So I just happen to know, because I've been mucking around, that 0.1 is representable in binary this way. You can actually see that I'm not calculating this out of the top of my head. I'm actually just following this pattern. This repeats, and this will repeat forever, much in the same way we have this pattern and this pattern. This is the binary thing that will go forever and a day. Now, that means that 0.1 can never be precisely represented as binary. You just can't. Just the nature of the two systems we're working with, it's impossible. At some point, you'll get to a thing and just go, that's good enough. We'll stop here. And that's accurate enough, but it will never be spot on. Never, ever, ever. It's just not possible. And right now, there are other systems which we can represent this information as, represent this thing. But as of this time of making this video in 2020, most computers and most systems we're dealing with will work in binary. So assuming that is your problem. Now, this hopefully starts making sense about where the inaccuracy comes from. But we mentioned earlier that there's a problem with large numbers. So let's flick to that and just look at large numbers. All right, so to illustrate this problem, let's use a couple things we've already done. Now, first of all, let's look at the previous number, which was 367.291. We glossed over a lot of how this is put together, but this number at the beginning, anything before the decimal point is perfectly representable. Like, there's never going to be a problem here. We can represent it precisely. It's the stuff after the decimal point that's the problem. Now, to make this a little bit even more simple, 291 is going to be a pain to calculate. We know what a tenth is, so 367.1, so 367 and 1/10 is going to look like this. Now, I'm just going to pull out the cheat sheet here. I've done this off camera, so don't think I'm actually adding these numbers up in my head. I kind of am, but no. So 367 looks like this. 1 0 1 1 0 1 1 1 1. Now, you wouldn't break this up normally, but it just makes it easier for this table. So this is 256 plus 64 plus 32, right? And that is 322. Yes, for the eagle-eyed, it's 352. I'll correct it, but I couldn't be bothered rotoing out my hand because it covers the digits often enough. This is what's it? These back three, 8 4 and 2. So it's 8 4 and 2, which is 14, and this is just 1. So that is 367. Right. So now after the bullet point, after the decimal point, we know what a tenth looks like. It's just now burned into our ancestral memory. It is 0 0 0 1 1. Add 0 0 1 1. And 0 0 1 1. And 0 0 1 1 as far as you care to run. Now I'm just going to stop there. Just going to quickly switch to another color. So to represent this number here, 367.1, we have actually had to, we'll just cut this guy off here. All right. We've had to use how many bits worth of information? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. 26. Right. 26 bits of information. We can continue to get additional precision by stacking on bits in groups of roughly 3. But we'll use 26 for now. Modern machines will probably use a lot more than 26. We're talking 32 and 64, but that's not important to this problem. So if we were to change this number from 367.1 to say, let's make it huger. 36,700.1. Already we're seeing that this is a precise representation of what we want, right? Now, the 0.1 is a tiny fraction of that, but maybe we care. So let's actually write this out. Now, I have actually pre-calculated this. I do not do this kind of stuff mentally, but it looks like this. 1 0 0 0 1 1 1 1 0 1 0 1 1 1 0 0. There's our decimal point, and we know at the back we have to go 0 0 0 1 1 0 0 1 1 0 0, etc., etc., etc. But let's say we only had 26 bits to play with. Where do we have to stop? Well, we have to get the 367,000 correct. So we have to have everything before the line, right? So that is 1, 2, 3, 4, and I've written in groups of 4. So 4, 8, 12, 16. We've used 16 bits here. Now we only have 26, so what does that mean? 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. You have to stop here. And as you can see, there is much less information between these two setups here. we've spent all our bits trying to represent the chunky bit of the number, which is important, because if you were to get this bit wrong, then you would just be like, it just makes no sense. You can afford to have rounding error at the back section, which is exactly what we've done. We've sacrificed some of it because we've got a large number. As this 367 increases and gets bigger and bigger and bigger, you're effectively having to steal information from the back end and bring it to the front here. And that is the reason why large numbers are going to be a problem. You can also get a sense of this intuitively in a way, because 0.1 as a percentage of this number is tiny. It's a smaller fraction than 0.1 as a percentage of this. Right? And if this number was 36,700,000, then 0.1 is an even smaller number of this. Why does this have an impact for us? Well, let's take an idea of, let's just say we have an axis in space. This is our pivot point for around which a cube is going to jiggle. It's the center point for, I don't know, some sort of cloud effect, whatever. And there's going to be some motion on it. So if this guy is centered at the origin, then let's just say, let's just look at the x position. So it's just moving left and right a little bit. So that's going to be x equals 0. Okay. We'll add some noise. The noise is going to be 1/10 of a unit. So it can range from 0 to 0.1. Great. We need some motion here, some jiggle. Cool. We already know this is a problem to represent precisely, but we can spend all our budget on precise representation of that. So if it's, say, 0.07, we will spend our bits on this guy. If it's 0.02, we'll still spend it representing that precisely. We're not spending anything on this value here because it's nothing. What happens if we took this entire system and moved it, to 30,000 units away? So our numbers are the same. Well, sorry, they're not the same. The numbers look like this. Right? And even though we care about the motion here, we don't care about any of this value. None of this 30,000 makes any difference. It just is. It's an offset. We care about this amount of motion here, the difference between 0.0 and 0.1, but we've already burnt a lot of our budget to represent and store that 30,000 number. And so this is where large numbers do pose a problem. So in practice, what you'll hear about is people say, let's say you're building a gigantic space opera where planets are at planetary scale. They're far away from the camera. Sure, you can do that, but rigs will probably be problematic. If you're rendering them out and you're getting a world position pass, they will likely be interesting. So these objects will be offset back to the center. So we'll take this and we'll know that, okay, that 30,000, whatever. We'll render it at this location. We'll get the full range of detail here, and then we just happen to know we need to add 30,000 later on. So hopefully that explains some of the underlying mathematical detail behind this. Now, there's other stuff we can look at, but we'll leave that to you. So I hope that made a little bit of sense to you. I've deliberately tried to keep it as generic-y mathsy as possible and in relatively straightforward terms so that you can get a sense of what's happening under the hood without worrying about the, the implementation detail. So if you are interested in the implementation detail, I'd encourage you to look at the specification called IEEE 754. Now I have this I have a link somewhere in the description below, which will take you to the actual official specification. And I think I'll see if I can dig out some tutorials that I think are a good representation of what's going on. So that is actually more around how things are actually mechanically or electronically plumbed under the hood. So if you're fascinated in that, definitely go down that line. The other thing that I sort of alluded to is that there are different ways to represent information. So obviously you might be asking the question about how can we possibly live in this world of high precision numerical calculations with this level of inaccuracy and weirdness? Well, the answer is we come up with different standards to solve them. So I will also see if I can find out some stuff. But the first thing I'd probably point you at is a Python package called decimal. This is probably of greatest interest because it represents a little bit closer to what you have in your head, I think, when you're writing down numbers on a bit of paper. And it will probably make, honestly, it'll probably make sense about how it works. So yeah, I guess that's probably all there is to say unless I go into super amounts of detail. Hopefully you enjoyed the video, and I guess ping me on Zoom, Zoom, comments below here, or one of the very billions of messengers I'm on. So yeah, cheers.